first of all, many thanks to Alexis and his whole team, to Jean-Marc for organizing everything, and also thanks for Davis for giving the general introduction. So I will take up many of the points that were already made here, but maybe from a little bit different viewpoint. So I originally come from statistical ecology, and so I hope this will be interesting. So let's. Is that? No. Oh no. Okay. So. So eventually we'll get the technique running. Okay, so this is from a review that we put out in 23. And the point of this, what I want to show it, is a little bit the development of methods in data science over the years. And what we wanted to point out with this time arrow is that the fundamental concepts of the statistics were developed sometimes between the 1920s, 1950s, when people were doing statistics with pen and paper. When the first computers arrived, or personal computers arrived, and people had access to computers around the 1980s, the first wave of machine learning happens, where all these fundamental concepts like boosting, bagging, random forests were developed. And then the last revolution that we're just in came with the emergence of GPUs, graphic processors that allowed to fit this deep neural network. And now we're in the middle of the second wave of machine learning, and currently, of course, all thinking about what can we do with these methods. So in ecology, we're looking around now, say what can we do with these deep neural networks. There's a lot of work on image recognition, segmentation, clustering, species recognition is a big topic. And of course, we can also use deep neural networks for regression type tasks, such as SDMs. So what is an SDM? I think in principle you're all aware of that, but I thought it's still useful to get everyone in the boat. So the typical idea of a correlative SDM is that we have observations, presence or presence absence of a species, and we want to correlate this to some environmental predictors. And typically this is something like temperature, but could also be soil, altitude, and predictors such as that. And so I thought it's important to point out, or if we go to these deep SDMs, it's important to point out a little bit the thinking that people had behind these models in ecology. So typically it was not the idea that we just want to predict where the species will also be on the map if you have some presence or presence absence record. But it was also the idea that these models estimate the niche of the species, so the habitat preferences of the species, so that we can look at the fitted model, and we get some ideas about under which environmental conditions do we expect these species to occur. And if we trust this type of model, we can also use it to project the response of this species under changes of these environmental conditions, which is called very important under climate or environmental change. And there is this long-ranging discussion in SDM modeling about what kind of niche are we modeling here. I guess most people agree that it will be the realized niche of the species, so that is not the true habitat preferences of the species, but the conditions under which this occurs, so it's the true habitat preferences plus potential dispersal limitation of biotic interactions and all this. And so there's this question whether these extrapolations really work, and a lot of people have worked on how can we get closer to the true realized niche by putting more mechanisms into this machine learning model. Damaris will talk in the afternoon, so maybe you should comment on this. But we are now still back with the correlative SDMs, and there we try to correlate the environment to the species presence. And so ecologists have followed all these technical developments that I had. So in the first SDMs that were first generation were statistical models, logistic regression or something like that. And then you fit these models, and then in the last years, second generations of SDMs, people have embraced this machine learning model, so it's by now standard that you use random forest or boosted regression trees, max-end, for this kind of modeling. And now we have the third generation, the deep learning models that are entering the field. And so we have to understand how do they compare in terms of performance and interpretability to this first and second generation. Maybe with a comment that many are already a little bit wary of the second generation models and feel that we have lost interpretability and that we're maybe already overfitting a little bit too much. And so if you try to sell this now to a person that is in SDM modeling and you're asking them to go into deep learning, probably a first concern of people is purely practical, and I say it's very complicated to build this model. Traditionally in SDM modeling, there's a lot of frameworks that people are using, and there's a relatively high level of support for people that want to do SDMs with softwares like MaxEnd. And so a typical SDM modeler might probably be concerned that's a lot of work to go into deep learning. And that's something we want to address with an R package, more on this on the workshop tomorrow. The CITO package that allows to fit these deep neural networks in one line of R code. So here you see the interface of CITO. For the example of present absence data set of the African elephant. And so you can write in R simply DNN, and then you write presence, depends on all the predictors that you have. There's a number of loss functions, including also statistical loss functions. We can bootstrap the entire thing to get uncertainties, and you can set it on different devices, CPU or GPU for training. And it's trained in the background in Torch for R, so one of the state-of-the-art machine learning frameworks. So then this R function will build the neural networks, you can plot it, and then you can warp. Then you can get the predictions, and if you bootstrap the entire thing, also the uncertainty on the map. Now, the second concern, people often say these deep learning models, they're too complex and they overfit. So it's very challenging for a statistical modeler to understand that if you have a model with millions of parameters, that they can actually work well. But the empirical evidence, and we will see this, I guess, over and over here in the talk, is that these models actually routinely outperform simple statistical models in predictive tasks, even for simple tabular data. And the intuition behind this, that there is a number of architectural features as well as explicit regularization features that these models have that avoid that they overfit too much. So in classical statistics, you always think about this bias variance trade-off, and the idea is that if you increase the number of model parameters, at some point you're reducing or you're increasing the fit, but reducing the uncertainty of the parameters. So in total, you need an intermediate model complexity, and this is something that we don't see in the deep learning models. So in the deep learning models, often if we make them larger, they start to generalize better again. A so-called double descent in deep learning, and so we have lots of evidence that we can deal with them. And again, so many parameters does not mean high flexibility. There's the simplicity preferences of the models that are built in. So we can see this in CITO. And here is a side note. One of these principles is that many of the machine learning models implicitly employ some kind of model averaging, so some redundancy in the networks and also in other methods that then lead to a better generalization error and an automatic model selection, something that we discussed here in this review paper 2018. So in CITO, we have a number of parameters that the user can use to do this hyperparameter tuning, to change the network architecture, the regularization. You can also include dropout and the learning parameters models, methods such as early stopping or learning rate schedulers. And then we also include in CITO options to do automatic hyperparameter tuning of all the model parameters under cross-validation. So you can, in the function, you can say, for example, here the learning rate of the model, tune it in a certain range, and will automatically run cross-validations to tune all these hyperparameters to get a good model performance. Now, the final concern that people usually have, to say that these models, they are black boxes. So they might predict well, but we have no idea what they're doing. And that's, of course, a big concern for using these models in real life, because on the one hand, I think ecologists want to have ecological understanding. On the other hand, if you want to use these models for policy support, for conservation, there's questions such as fairness, transparency, ethical AI. So will people believe what they're doing if they can't understand how predictions are made? So will they believe that they should move a conservation area to the north because of climate change? It's not clear really how the model makes the prediction. And so it's been pointed out by many people that this black box idea is a little bit wrong. It's not really, the box is not black because we can look at the machine learning models, we can see each of the weights. The problem is that it's just complicated. So many people have called this a gray box. The challenge is somehow to get methods that look into this box and that simplify them again so that we can interpret them as humans. And so this is what the field of explainable AI is looking at. We had a review paper in Ecography on explainable AI for species distribution models, 2018, I think. And here we pointed out again for this example data set that we had here for the African elephant. It was fit with I think a random forest model at the time. There's different types of methods that we can employ. On the one hand, so-called global explainers that look at the overall variable importance. So you have something like permutation importance, or you can look at partial dependency plots. Here, where you see what's the response of the model or the predicted probability to one variable. And then we have so-called local explainers that look at what's the reason for making a particular prediction at a particular site. And so we have also implemented many of these methods readily in CITO. So if you fit the DNNs with a CITO package, here is an example of fitting a very simple regression. This is how you used to with a linear regression, and this is how you call the model with a CITO package. So it's exactly the same. This is the regression table that you usually get out in a linear regression model, where you have your effect estimates and your standard errors and your p-values. And in CITO, we calculate something very similar. So these average conditional effects, so the average derivative across all data points. And so we bootstrap them, so we also get the standard error and the p-values on them. And we showed that at least for simple models, these are relatively valid. Let's put it like this. We can, in a standard regression, you can get these effect plots where you see the effect of a predictor on the response, and we can get the same with CITO. So that's the average local effect plots, including uncertainties from bootstrapping. And in regression models, you're used to ANOVA, where you look at what's the importance of a particular variable, and we get the same here in CITO, where we randomize certain variables, and we get the importance for the predictions, and again, p-values from bootstrapping that may or may not be valid depending on the exact structure of the data. So what I wanted to show you in this first part is that in principle, machine learning and deep learning models, our neural networks, they can be used similar as simpler statistical models for tasks as regression and classifications. They're not so different for GLMs and GAMs when you use them for SDM modeling. So similar to Davis, I now wanted to ask Zach, but okay, why should we do it? What are the advantages if we actually apply these architectures to SDMs? And also similar to Davis, and I think that's kind of the obvious thing, the main advantage, first of all, is that you can not only use tabular inputs, but you can use images and other complex data as predictors. Before in the standard SDMs, where we have to represent predicted data as tabular data, so a number of numeric values. With deep SDMs, we can also use complex data. So, for example, images, and we could test. This is just an example. If the elephant really likes this type of landscape patterns, or if you'd expect the elephant to be present in this kind of landscape patterns, or maybe you have sound recorders everywhere and you can look at the soundscape and you can test if your species prefer a certain soundscape to be present or not. So all of this is possible. Here's an example from a master thesis in my group that looked at the British butterfly survey. And so we have presence-absence records from this British butterfly survey across all of the UK. And so we try to predict with such a deep SDM using both climatic time series and optical satellite data. And we compared this to random forest and standard fully connected DNN with bioclim variables. And yeah, we see a slight outperformance of the deep neural network, in particular for the time series. So we see the larger outperformance for the time series data. Here is this per species, and we see something that many people have reported. So the rare species seem to profit more from this deep SDMs than the common species, which seem to be easier to predict from both types of data. And we can, in principle, also for these images, we can use XAI, explainable AI, to look at which aspects of the time series then led to the classification. So these are this is shown the raw gradients, or some people also call this vanilla gradients, whether you had a positive or negative contribution of each pixel of the time series to the prediction. It's obviously difficult to interpret here, so you see nothing really. It seems to be a complicated pattern, but in principle you can look now at the image and see which kind of aspects of the image led to these predictions. So we're currently trying to build all these features also into CITO. So the development version of CITO also contains a CNN function as well as a multimodal function that can mix several CNNs with fully connected neural networks. So as an example here, we used the bird clef Kaggle competition, where the goal is to recognize bird species from sounds. So the sounds are represented as images. And we additionally used, we have the longitude and the latitude of the image, so the location. And so we try to see what's the performance in classifying the bird as a baseline model, just a DNN with location. And then as a CNN, we have here a standard convolutional neural network with transfer learning using the mobile net data set. And then in CITO now you can build, if you have several CNNs, you can build them all together in one function so that you get a multimodal model and run it. And then you see, of course, what you expect, that there is a big outperformance to actually listening to the sounds rather than just taking the location of the sound. And we see a slight increase of the multimodal network, which is, yeah, but very, very low. But that's also due to the fact that the CNN is already pretty good at classifying the birds. Now, So this is one of the clear advantages. We can use the images. The second clear advantage, or maybe not so clear, but a potential advantage, is that, well, also Davis already mentioned, that the deep neural networks can very easily be extended to community modeling, which is a big interest in SDM modeling. So traditional biodiversity monitoring is due to single species presence only observations. And we argue in this recent perspective paper, which came out in Trends in Research in Ecology and Evolution last year, that this will change with the new sensors that are emerging in the new biodiversity sensors. And we're thinking particular about molecular sensors, so eDNA, but also acoustic and visual sensors that, coupled with AI, promise to deliver data in the future that is always community data. So you will always get information about the entire community. And so what we argue in this perspective, there is a need for methods for SDMs that are fundamentally community SDMs rather than single species SDMs. And so there are already community SDMs that people work on in statistics for a long time, and these are the so-called joint species distribution models, jSDMs. And I wanted to give a quick introduction to the statistical side before we jump to the machine learning side. So a simple SDM basically relates the presence or presence-absence of the species to an environment. And then people were, of course, for a long time interested in predicting entire communities and also species diversity. And one of the, it's a bit weird here. Okay, let's see. So the standard approach is that you basically just stack your SDM. So you run just a large number of SDMs, and this trivially predicts your entire community. So this was done a lot, and there is an extension of the stacked SDMs that also people have explored abundantly. They're called multi-species SDMs, and in multi-species SDMs you don't fit SDMs independently, but you connect them, for example, by random slopes on the species effects, so that species can learn from each other, so that you can share information between species. And so the latest extension to this are the so-called joint species distribution models, and they are multi-species SDMs, so they can share information between species. But there is an additional component, and this additional component is a residual covariance matrix. So you're additionally fitting the tendency of species at the same environment to occur more often together than you would expect to by chance, or less often. So if you have a joint species distribution model, you can say, conditional on the fact that one species is present here on the side, it's also more likely that the other species is present, or less likely at the same environment. Yeah, so already subtracting for the environment. And as in other models, we can also add a spatial component to this, and this gets this full-blown a jSDM structure where you model the species as a function of the environment, the space, and this covariance component. So this is the full picture again, and ecologists are so interested about this picture because now if you run an ANOVA on this kind of models and look at the contributions of these three components, you get this classical BAM diagram that fits to the theory of ecology that says to find species together at one point, they have to come there through space, so that has to be actually accessible, the environment has to be suitable, and then the competition has to be so that it's not excluded by other biotic interactions. And so what we pointed out here is in this paper, the internal structure of meta-communities, that you can even further subdivide the structure so that you look now at the contributions. So the jSDMs allow you to partition the contributions of the presence into environment, space, and also the associations. And you can further subdivide this per species, but you can also subdivide it per site. And then you can look at the sites in space and look for which sites is the contribution or the community more driven by environment, space, or a covariation. So I want to give you a case study of this for an eDNA a survey of ponds in the UK, in England, in the area of Oxford. So we have 320 ponds. And we have eDNA data for 15 aquatic and 48 terrestrial species, and I will mostly concentrate on the aquatic species. We have covariates of the pond characteristics, and then we run this jSDM, and we can, for example, see that the amphibic species are more driven by the covariance and the environmental component, whereas the fish, they are more driven by the spatial component. So they seem to be, the community composition seems to be more driven by the spatial component. And we can also look at all the ponds and see how the assembly mechanisms change. And so just as, maybe just as one example, we can see that with increasing pond area, the importance of the environment increases compared to space and the co-distribution for explaining the species composition. And we can look at the same for traits. So for example, we can see that fish have a higher biotic component, so fish are more sensitive to other fish in terms of the species composition, whereas birds, for example, in this data set are more driven by the environment. So many of these or all of these methods are available in a package that we also provide, the jSDM package. The motivation for this package is that statistical jSDMs are very slow to fit because the likelihood is very complicated to implement. And so jSDM uses a Monte Carlo approximation of the likelihood that we fit in PyTorch in the background on the GPU. And that makes the model extremely scalable, so we can fit 1,000 species, or a large number of species, which is what you get when you work with eDNA data, 30,000 sites in about 5 minutes on a GPU, which is very fast for a jSDM. And so if you want to try this model out, you can install it directly. Now, this is the existing framework that we have in statistical species distribution model. And of course, it's interesting now, and that's something we're interested in, is to look at which of this can we take over to the deep SDM area. So in principle, with a deep SDMs or neural network, it's very, very easy to implement multi-species models because you can just take your predictors in, and as we saw, you can just, instead of having one species that you predict an entire community as output. And in situ, you can do this directly as you see here. And if you run this in situ, you will get your niche estimates for all of your species together instead for a single species, including the XAI and everything that we discussed about. The interesting thing is now to understand better for us at least, to which extent do these multi-species deep SDMs maintain the statistical properties of joint species distribution model, and so in particular the sharing of information between species. So what we see is that they often outperform a little bit, and in particular for rare species, they work a little bit better than the single species deep SDMs, and so there seems to be some sharing of information. And so we also have, we can see that it depends on the model architecture, how much information is shared. There is this question is, can you make conditional predictions? So if you know that some of the species are there, can you improve the predictions for the other species? You can't with a standard DNN, but I suspect, for example, with Davis transformer structure, you could, and I'm not sure if you have already tried it out. And there is this interpretation of the XAI that I think that ecologists are very fond of, is this separation of environmental effects versus covariance that we haven't fully taken over to the deep SDMs. So so what I wanted to show you is, I think for the selling point for the deep SDMs is on the one hand we can build models with very complicated predictors. We can build multimodal models, we can build community models, and we can probably enforce the sharing of information. And the advantage, of course, of the deep learning frameworks, of the machine learning frameworks in general, that you have this automatic model selection feature, so you have to take much less care about selecting the right covariates in principle, at least for prediction, than you have in classical models. So in the last part, so I promised a few issues, and I want to concentrate on 3 issues that I think are still a problem: is interpretation, validation, and then causality. So the first is the interpretation, and so my view is, although traditionally in machine learning we care very much about predictive performance, I think ecologists, in the end, for deep SDMs to be successful, they need to be interpretable. Ecologists will want to see what are the predictors that really lead to the presence of a species, and these predictors need to make sense somehow. So for simple, fully connected neural networks, I showed you a few of the XAI features that we have. And I think we're pretty happy with them. I think they are at a level where people can use them, and it gives them useful biological information that can be interpreted. And we can also show that they map reasonably well to statistical methods, so that we get some correspondence to these methods. For time series images, I still think there is a problem with the XAI, so we don't really have good XAI for these methods, and so there's probably a trade-off between having models that are interpretable and predictive. And so what we would want ideally would be something that we have a translator that says, this picture tells you that with high certainty this butterfly requires warm winters with medium levels of precipitation, and with low certainty it avoids sites that are very dry in summer. But we don't have that at the moment. The second issue I see is, can we really trust these validation errors that are reported? There was already a question about validation errors. And so in principle, validation of these methods is very simple. You just take some holdout and you look at the performance on the holdout. But in practice, there is no truly independent observations, as we point out in this paper here in ecography. And the data that we have in ecology are always spatially, temporally, and so on structured. And so we made a bunch of simulations in this paper, and the conclusion was that simple cross-validations are really overly optimistic. And so you select overfitted models, and you need blocked approaches to get realistic validation errors, which is sometimes, however, not so easy to achieve. So here's one example with phylogenetic blocking, where we show that if you don't block properly phylogenetically, then you will select the wrong model, an overly complicated model. And I think this is particularly concerning with this kind of images, because we see from many other fields that these images are very easily overfit. In the aftermath of COVID, we got a lot of papers that came out now to look at the performance of these models that were fit on to detect COVID. And here in this paper, they show that in the published papers, they report basically perfect performance, all of these models on image data. And retrospectively, they were fit again on new data, and the performance dropped enormously, showing that they're really overfit. And there's a bunch of reasons why this happens. But I think there is a big tendency that if you don't really get independent validation data, which images is particularly difficult, there's a big danger to overfit. So you need to properly establish holdouts. I think it would be useful to do more on simulated data, and there's also baseline models, because we know already that SDMs could potentially overfit. I think this is a very interesting study from Ban and McGill, 2007, and this is still for standard first machine learning generation models, GAMs and BRTs. They compared the performance of species distribution models with environmental predictors to the performance at models that only had X and Y position. And they showed here that often the models that only had X and Y position performing at the same level or better in random cross-validation than models that get the environmental predictors. And so they said that we're not really sure if these environmental predictors, if they're actually causal, or if they're just a complicated way to model space, so that we can basically model blobs on the landscape. I think there's still, even further before deep SDMs, there's some doubts if these models are really getting the niche right, or if they just fit a spatial pattern. And that leads me to the third issue that I wanted to highlight is, are they predicting the right things for the right reasons. And so it's well known that there's often a trade-off between building models for predictions and building models for inference. We know in statistical models, to get causal effects, we need to select the right predictors. So if you have confounders, you have to put them in. But if you have other variables such as colliders, if you include them in a regression model, you will get biased estimates. And the important thing about colliders is if you have them, they will bias your causal estimates, but they might still be excellent predictors to predict the signal. And so the same is in machine learning. So some people, and for example, it's a nice paper by Zhao and Hasty, pointed out if you feed just all your variables to the model, and some of them are colliders, you will inevitably get the wrong effect. So in principle, to even have a chance in machine learning to get the right effects, you have to select your models in the same way that you would do in causal inference. But there's a second problem, is even if you feed the right models into the right predictors into your model, in a linear model you will usually be able, if you have collinear variables, you will be able to separate which is the right predictor unless they're perfectly collinear. So this is not the case in machine learning models because of all these regularization methods that we employ. So this is just a very simple example for elastic net regularization. So if we have here an example where we have one variable that is the actual effect, the other variable is collinear but has no effect. If you employ regularization now, it will push the variable or parts of the effect to the other variable, and that's what we call causal spillover. Now, we looked at this in detail, and not all machine learning algorithms show causal spillover to the same degree. So one of the worst is actually the random forest. And the reason is that the random forest is always, at the splitting, is always hiding parts of the features from the model. And so if you have two collinear features and you're always hiding one, it will move it to the other. And so if you have one variable that is actually having the effect and you have another variable that is collinear, the random forest will tend to distribute the effects between the two. So we tested this, in short, we tested this for all the standard machine learning methods, and the paper is here available on the archive. And we found that actually the neural networks, they perform best in separating collinear features as long as you don't employ some regularization features that lead to redundancy. For example, if you turn on dropout, it will smear out the variables again, and you will not be able to identify the true causal variables. And so you could say it's very theoretical, but for the way people are using machine learning models, this has implications. And so one is, of course, this idea that if you want to predict under climate change and your variables under climate change have a different collinearity structure, and if you haven't identified the right variables, you will make the wrong decisions. And we showed this here in a simulated case study, the difference between a model that is tuned for prediction and a model that is tuned for inference. So we have here a hypothetical case study with a few variable connections and a collider. And so we tuned a machine learning model, or we tuned machine learning models, random forest, boosted regression trees, and neural networks, providing them all variables or providing them only the variables that you would include for causal model selection. And here you see for making predictions, so in distribution, the best thing is to just provide the machine learning model all the variables, and then you will get the best predictions. But if you want to make predictions under a changed collinearity structure, then the models that where you provide all the variables, they do really, really badly, and the neural networks actually do that are causally selected, so that only get the causal variables, they do best. So so what we can conclude from there is that if we tune the models from predictions, they will usually outperform in distribution. But if we do stuff like predicting under climate change, we might get a problem with this type of variable selection, and it might be better to tune for inference. So the conclusions of this last part is that I think we need meaningful XAI, and there's probably at some point really a trade-off between interpretability and predictive performance. I would suspect that we that we have problems with the performance evaluation. So I think the performance is probably that we get in the studies is usually optimistic. And if we would get real independent holdouts, would see that these models generalize worse than we think. And probably part of this is because if you feed just all the variables into a model, there is a big danger that you overfit, and it might be what you want. Because if you just want to spatially interpolate and see where the species are at the moment, might be perfectly fine. But probably people will want to use these models also to predict responses under climate change. And then we have to be much more careful about all these causality questions. So I hope I could show you that these models are not completely new, but they are in a history of development from statistical and earlier machine learning models. But that the deep species distribution models, they offer exciting new opportunities that we should explore. And for me, really the one main point is that we can process this large number of input data. But I think we have to be careful about performance, interpretability and causality. So all of these problems, they were already there in the previous generation of SDM modeling. But I think they are even more concerning for the deep learning models, when we have these large models that are much more difficult to interpret. So yeah, thank you very much. Sorry, a bit over time, huh?
Yeah, but it's
sorry.
The break was long, and we had some technical issue at the beginning, so yeah, that's fine. Is there any question for Florian? Yeah, Christophe.
Thanks, Florian, for the talk. I found really interesting and useful that this effort of making deep learning model building available in R for ecologists with the package Cyto. And I found especially interesting the effort of translating in a statistical language some interpretability outputs of models. I was wondering specifically for what you call the ACE, which, if I understood correctly, is a type of effect size related to a certain type of input. What is it exactly? And specifically, if it depends on the correlation structure of the input variable with the other inputs?
Yeah, no, so it's basically the local derivative, so the conditional effect calculated at each data point. So it's the effect of variable x conditional on all other variables at each data points, and then we average it. So in statistics, it's also called the average marginal effect. And one of the advantages is that it's not sensitive to collinearity. Yeah. So.
Okay. Okay. Thank you. And second question about Cyto, while I have the micro,
yeah, sure.
Is like an advantage of Torch is its flexibility to build complex and composite models and likelihoods. I was wondering to what extent, and you have shown, like, for instance, you can build multimodal models, which is nice. Can you also build, for instance, integrated SDMs with Cyto, which is where the likelihood is composites, where you want to connect to different types of data, for instance?
Yeah, maybe. So, maybe as a side note, so what we're using, so we had previous packages that were built on PyTorch, but Cyto is using Torch, so this Torch implementation for R, so it doesn't require a Python installation, which was from the user feedback that we got. The Python installation it's a nightmare because users get so many problems. And so we're very happy to have now the Cyto package, and it's basically just the front end for Torch for R. And Torch for R is somewhat more limited than PyTorch, but I think in terms of portability, a very nice framework to consider in general. So in Cyto, you have the modules that we have, and what we have is an option to build a custom loss function. So you can use the loss functions that we have. So we provide all the typical machine learning loss functions, MSE cross entropy, but we also provide the standard GLM loss functions like binomial Poisson that people are used to. But you can build in custom loss functions. And so as long as you can formulate your likelihood as a custom loss function, that's probably okay. But if you want to do something complex where you have latent variables that you want to integrate out, which you maybe would like to do if you want to do something like an occupancy model inside, then it will get difficult. So as long as it's just three types of integrated in the sense that you have three types of, let's say, presence, absence, and presence only data, I think it would be possible now. If you want to do anything that requires integration of latent variables, it won't.
Thank you.
Hi, thank you for your talk. I have one question. In eDNA data, one main question is the sampling efforts have been done to have some information. And sometimes for me, such strategies look like miraculous. And do you think it's possible to learn on the offset? And the best way to calculate the offsets or sampling efforts for eDNA using, because usually it's based on to divide it by the full abundance or something like this, so it's completely crazy. So do you mean that we can infer these parameters?
Yeah, so I don't know, like it's of course a big topic. So at the moment I have to say our collaboration with the eDNA people, we basically took the eDNA, the data, basically the species list as we got this from them. But of course the sampling effort, so false presences, false absences is a big topic, and there's a number of people that try to extend jSDMs to kind of occupancy jSDMs, where you include the sampling effort and include false absences, false presences for the eDNA data. And for the SJSDM package, we have also thought about extending it, but we haven't worked on this yet. But I mean, there's a number of papers already out there for occupancy, basically occupancy, jSDMs, and yeah, that's what I would say. People are working on it. I'm not sure how important it is in the end if you have standardized sampling effort to actually deal with it personally. Or whether you can just, as long as the sampling effort is standardized, if you can just use the species list as it comes out of there.
And thank you to insist on the problem of predictions, co-structure, spatial structure, and so on, because it remains a true problem in the community.
Thank you.
So, last question.
So thank you, Florian, for this amazing talk. I was just wondering, when you use explainable AI techniques, there are many tools now available. Have you ever found contradictory explanations from different tools? For instance, if you look at global importance, there are many ways to quantify that. And did you sometimes find inconsistent results?
Yeah, I think they all give you different results, right? So. Yeah, let me maybe go back here. I mean, I worked in the beginning of my career. I worked a lot on. So I worked a lot on simulation models, and there you have this field of sensitivity analysis where you're trying to see how sensitive is the model to changes in the input, and you have like 300 methods, and they all gave you different results. That's what I think what people concluded, and I think the same. I mean, in the end, XAI are sensitivity methods. You're trying to change an input, and you see what is in the output. And I mean, there's many well-known problems with this. So, for example, with the feature importance that we do, the standard permutation feature importance is very sensitive to collinearity. And so it will definitely give you, I would expect that it will give you different results than the ACE in terms of the strength of the variables under collinearity. So yeah, I think like our solution so far was maybe not to provide people with a very large range of methods, but provide them with 3 or 4 methods that we think are fairly commonly used. So the ALEs, which are I think very common, the feature importance, which is very common, and then the ACEs we included because we wanted something that maps on effect sizes in a statistical model, and we think it's the closest to it gets closest to an effect size in a statistical model. And so we were trying to replace basically the standard statistical stuff, but there is hundreds of methods and they all give you different results because they measure different things. It's not wrong that they give you different results, but probably you really have to, you cannot just run one of these methods and then say that's the effect, but you have to understand what they really measure.
Okay. Thank you very much.
So, thanks a lot again.